Our second application for quadratics involves a sport example. You throw a baseball straight up in the air at a velocity of 45 feet per second. You release the baseball at a height of 5.5 feet and catch it when it falls back to the height of 6 feet. The height of the ball can be modeled by this function. H of t equals negative 16t squared plus 45t plus 5.5. So notice that 5.5 corresponds to the height when the ball was released. 45t corresponds to the velocity. We have a few questions to answer, and we will be collecting our information in the table and then graphing all of the ordered pairs that we generate. Our first question is to find the y-intercept. We find the y-intercept of the function when we let the input value equal 0. So for step 1, we're going to evaluate the height when the time is 0. So h of 0 would equal negative 16 times 0 squared plus 45 times 0 plus 5.5. So negative 16 multiplied by 0 quantity squared is going to be 0 and eliminate. 45 times 0 eliminates, and that leaves us 5.5. So the ordered pair we've just generated is a time of 0 had a height of 5.5 feet. So 0, 5.5 is our first ordered pair. In question 2, we'll determine the vertex point. Remember, x is equal to minus b over 2a when we're looking for the x value of the vertex point. So the value of a comes from that first coefficient. B is that second coefficient. So looking for vertex, x would be equal to negative times a b value of 45 divided by 2 times a. So 2 times minus 16. This gives us negative 45 divided by negative 32. So we notice that we have a negative divided by a negative, and we're going to use decimals for this problem, so that will make it easier for us to plot ordered pairs that we generate. So using our calculator, 45 divided by 32 is positive 1.4. So 1.4 is going to correspond to the input value of that vertex point, or our time. Now we're going to use 1.4 back in the function to evaluate. That will generate the output, or height, of the ball. So the height as a function of 1.4 seconds is now equal to negative 16 times the quantity of 1.4 squared plus 45 times 1.4 plus 5.5. Using our order of operations, we'll need to square 1.4 and then multiply by the negative 16. Following the order of operations, we want to take the quantity of 1.4 and square it. Once you have that total, multiply by negative 16. Then you're going to add 45 times 1.4. And last, add 5.5. Our output here is going to be 37.14. So when the input value of 1.4 seconds is used, an output value of 37.14 feet is the output. So here's another ordered pair we've generated. For question 3, how much time passes before you catch the ball? So read this carefully. If we're looking for how much time passes when we catch the ball, at what height are we catching the ball? So this is where we have to go back to the scenario and notice where it says that it falls back to a height of 6 feet. That's when you're catching the ball. So we're using a height of 6. 6 would equal our quadratic function. So 6 equals negative 16t squared plus 45t plus 5.5. We'll need to put this in standard form, in other words, equal to 0, and written from highest to lowest power. So it looks like we'll need to subtract 6 from each side of the equation. And then we'll have 0 equals our quadratic equation. Negative 16t squared plus 45t And then 5.5 minus 6 is going to give us negative 0.5. We probably don't even want to consider factoring this, so we're going directly to using the quadratic formula. So our value of A now will be negative 16, B would be 45, and C is negative 0.5. Using the quadratic formula then, negative times B plus or minus the square root of our quantity of B squared minus 4 times A times C. And all of those terms are going to be divided by 2 times A. That gives us 2 times negative 16. Simplifying, we've got negative times positive 45. That gives us negative 45 plus or minus what's under the radical. So we're going to first square the quantity of 45, and that gives us 2025. And our three factors are negative 4 times negative 16 times negative half. Since we have an odd number of negatives, we will be subtracting. Let's do the multiplying. 4 times 16, and then that product would be multiplied by 0.5. That gives us 32. So we'll be subtracting 32. Our divisor, 2 times negative 16, is negative 32. So now we have x equal to negative 45 plus or minus the square root of 2025 minus 32. And that's going to give us 1,993, all divided by negative 32. Since we need a decimal value for this radical, use the square root function on your calculator. And I'm going to round to the nearest tenth, and that will give me 44.6 for that radical equivalent. So we're generating two solutions here. One solution would be x equals negative 45 minus 44.6 divided by negative 32. And the other will be x equal to negative 45 plus 44.6, all divided by negative 32. When we use subtraction, we end up with 2.8 seconds. And when we use addition, we end up with negative 0.0125. Is it possible to have negative seconds? So that answer needs to be eliminated. It doesn't make any sense. So the x value of 2.8 seconds does work. So I'm going to go back into the table here and use just the positive 2.8 seconds. And that corresponds to that height of 6 feet when we're catching the ball. With question 4, it asks, when would you expect the baseball to hit the ground if you did not intend to catch it? So if it hits the ground, that means the height is 0. Height of 0 equals our quadratic function. So again, we're going to use the quadratic formula, but we have different values for A, B, and C this time. A at negative 16, B is 45, and C would be 5.5. So our evaluation this time, x would equal negative times our B value plus or minus the square root of our quantity B squared minus 4 times negative 16 times 5.5. And all of these terms would be divided by 2 times A. That would be 2 times negative 16. X now equals negative 45 plus or minus, under this radical now, 45 squared. We've already worked with 45 squared in the previous question, so we know that's 2025. And we have our three factors, negative 4 times negative 16, but this time it's multiplied by 5.5. We have a negative times a positive, so we're going to be adding something to that 2025. And that amount is 352. And all of these terms are divided by negative 32. To simplify what we have under this radical, simply add 2025 to 352, and we'll have 2377. Again, we need a decimal equivalent in order to use this and plot it. So I'll use the calculator function for square root to get that decimal equivalent. And that amount is about 48.8. So one x value would be negative 45 minus 48.8 divided by the negative 32. And the other x value will come from addition. Negative 45 plus 48.8 divided by the negative 32. When we use subtraction, we'll end up with 2.9 seconds. 2.9 seconds sounds possible. When we use addition, we'll end up with a negative 0.1875 seconds. Now, negative time isn't possible, so that answer would be one of those extraneous solutions. So we're only going to transfer 2.9 seconds into the table. And remember, that height was 0. That's when the ball is on the ground. Again, for part 5, we'll state domain and range once we look at the graph. So we're ready to plot our ordered pairs, think about how to label and title the axes, come up with appropriate scales. Our input values, t is time in seconds, and only positive numbers or 0 would make sense for time. The output is height in feet, and only positive numbers or 0 also makes sense for that. So we're just going to use the edges of our graph. So we have t for time in seconds, and our other axis would be along this edge. This is our height in feet. We start with 0 for the scale, looking at the values for input time. Our largest is 2.9, so we could spread this out a little bit, maybe counting by 0.2. So 0.2, 0.4, 0.6, 0.8, here would be 1 second. So 3 is as large as we need to go. Considering height, 37.14 is our largest number, so I could just count by 2s. And now we're ready to plot the ordered pairs. Our first ordered pair is 0, 5.5. Our next ordered pair is 1.4, 37.14. So our scale was counting by 0.2, so this line would be 1.4, and I'll go up to just a little past 37. Our next ordered pair is 2.8, 6, so that one's a little easier to plot. And finally 2.90. So just before 3. Now you can see the maximum point of our parabola and how it's opening upside down, and that's all because our lead coefficient, remember, was a negative number. So let's connect our ordered pairs and we'll see the parabola. Might be a good idea to label that vertex point of 1.4, 37.14. And then connect those ordered pairs. Now if we consider dots versus arrows on this graph, if we continue going to the left from our y-intercept, we would have negative time. So we keep the dot. And think about what this x-intercept represents. That's on the ground. You can't go below that and measure with negative numbers. So we do keep the dots on both ends of our parabola. Our final item is to state the domain and range for question 5. So our domain is input, that's time. The shortest amount of time, remember, would be found here at our y-intercept, that's 0 seconds. The largest amount of time would be represented when this baseball hits the ground, so that's our 2.9 seconds. The range involves the height of the ball. So the lowest our ball will ever be is when it hits the ground, that would be 0 feet. And the highest point for the baseball would be that vertex point. So the height involved there is 37.14. Notice that we're always writing domain and range from the smallest value to the largest value. It's always this order. So when you're thinking of writing interval notation for domain and range, it's always starting with the smallest value and ending with the largest value.